Hey guys, just want to quickly run through today's notes with you here. Um, Pressure, and by the way, all of these notes, it is somewhat of a rehash. You do have a lot of prior knowledge on this, especially from chemistry and somewhat also from your ninth grade physics class. Pressure is one of the things we talked about in ninth grade physics more than likely. It's force per unit area, or pressure, lowercase p, equals F divided by A. Now, a few things to note here. Pressure is measured in pascals. Now, a pascal is a Newton per meter squared. Now, a Newton is very, very small, and a meter squared is a huge distance or a huge square area or a huge area. And so you actually, Pascal is very, very, very small. We're generally going to measure our pressures in kilopascals. And so you'll have to do times 10 to the third to get back to your base unit of pascals. Force per unit area, that's basic things for all of your math. The only thing that you might see happen is that your areas, you might have to put in things like pi r squared if it's a circle, right? Or something else there, depending on what you actually have area wise. Um, Pressure explains why whenever you have a balloon and you tap it with a pin, it doesn't take very much force to cause it to pop because your area is so small. Same thing with a shot, right? The area, the surface area of a needle or a pin is so teeny there, area small, that the amount of force you have to exert to actually have a high pressure is very, very small as well. It also explains how pneumatics work. Over here is a incredibly basic idea of a pneumatic. What you do is you have a very small surface area and you have liquid or fluid, some type of fluid on the inside, and you have one side that you're going to apply force to that has a very, very small surface area, and then you have another spot which has that's allowed to move, a piston, that has a very large surface area. So if you put on the small surface area, you only have to put a small force in. But since pressure inside of a fluid must be equal, for the large surface area, what you end up having is a very, very large force out. All right, now let's get into something that you are already familiar with from chemistry, the mole. Mole is the amount of substance, same number of particles, carbon, 12 grams, right? It's 6.02 times 10 to the 23rd atoms or molecules. It's also the molar mass in grams. Let's actually open up a periodic table here just so we're all tracking on the same page. It's kind of cool here that for the periodic table, that you have these molar masses down here, like oxygen's molar mass, 15.99994, or about 16, right? Here, about 16 AMUs, if we were talking in atomic mass units, or if we're talking about for the mole, 16 grams is the molar mass. And we'll use capital M, lowercase m, maybe for molar mass. In other words, if you get 16 grams approximately of oxygen, you'd have 6.02 times 10 to the 34th, times 10 to the 23rd, excuse me, number of atoms there, of oxygen atoms. And if you had O2, for example, you would need 32, 16 times 2, 32 grams to have the same number of molecules, 6.02 times 10 to the 23rd molecules of O2. In other words, it works, and maybe we should actually write that out here. O for oxygen, to get 6.02 times 10 to the 23rd number of atoms, you would just need 16 grams. But for O2, now that's a molecule, two oxygens joined together, you would need 32 grams. For water, H2O, I would end up needing to add my oxygens with this hydrogen over here, which is about 1. So I would have 2 hydrogens, that's 1 plus 1, 2, plus the 1 oxygen, that's 16. I would need about 18 grams to have that number of molecules, a mole, 6.02 times 10 to the 23rd molecules of water. So here are your equations that you are already familiar with, and this first one's given to you in the IB packet here. This N number of moles equals capital N number of molecules divided by Na, or Avogadro's constant there. The one that you are also familiar with from chemistry but is not given to you in the packet, number of moles equals the mass divided by the molar mass. Now, let's talk about equations of states for gases. Now, an equation of state means that we're not talking about changes in volume, changes in pressure here. This is just one instant, everything one constant number. The equation you learned in chemistry that you'll also use here in physics is the ideal gas law, PV equals nRT. Just be careful. In chemistry, you probably didn't use a volume of meters squared. You probably didn't use a pressure of pascals, and your temperature might have been in degrees Celsius instead of Kelvin, which means that the constant is a little bit different in our case. We want to use pascals and meters squared base units for the SI system. Also, because of something happening in the future, pressure times a change in volume is going to equal work. We're going to end up learning that in the option B that we're going to end up doing the engineering option. Notice also the unit here, joules per Kelvin per mole for that gas constant there. So PV, a Pascal times a meter cubed, ends up having the unit, the combined unit of the joule there. It's alluding to the idea of work and of energy that's actually occurring. We could also write that ideal gas law in terms of number of molecules. And this one might not be as familiar for you. We're going to use the Boltzmann constant, R divided by Avogadro's number. PV equals capital N, standing for number of molecules or number of atoms, times Boltzmann's constant times temperature. All right, flying through this because all of that is mostly plug chug there. The kinetic theory of an ideal gas is something that you have already probably taken notes on. If you haven't taken notes from the book, you need that. And I just kind of want to summarize this for you. You already have all the specific assumptions that's made. But basically, to try to model a gas, we say, you know what? Let's forget things that don't really matter. Let's forget all the intermolecular forces. Let's forget all of the other little details inside of it. The gas molecules are moving around really fast, and there's a whole bunch of them. They're running into stuff. So it's almost like, you know what, let's go back to topic 2, mechanics, and let's imagine that every last gas molecule is a little bumper car. And they're zooming around and they're bumping off of each other. And pressure is just force being exerted on the walls of the container there, because literally those little bumper cars are ramming into the walls of the container. And there's so many of them, they're ramming into the walls of the container all the time, exerting what ends up averaging out to give you kind of an equal uniform force. So we call that a uniform pressure. To have that, you have to have a large number of particles, and they have to be moving all over the place in random motion. They need to be so small that we can neglect their size. And they have to be moving all in random directions, so the directions have to average out. Every collision is perfectly elastic, which then lets us talk about here this idea of impulse, right? Each molecule produces a force on the wall container. Force equals change in momentum divided by time. Whenever they hit the walls, they bounce backwards with the exact same momentum as another assumption that we make, just the other direction, negative. And so each molecule hits the wall, produces force, and that creates uniform pressure. So check out all of those assumptions. Make sure you have those down in your notes. Except the book has a better form here. I'm trying to summarize down for the sake of understanding. I have seen IB questions come up where they say things like, "Hey, give us 2 of the assumptions of the kinetic theory of an ideal gas," or give us 3 of the assumptions of the kinetic theory of an ideal gas, and you just need to list out 2 or 3 of them, however many they ask for. Now, all of that was mostly review here. And then you're plugging and chugging through equations, right? Not a big deal. Ideal gas law, what is a mole? Maybe you've got to dust off a little bit of chemistry knowledge, and we went through this quick, and you're like, oh my goodness, but I can figure that out. But whenever we get to this idea of the mean kinetic energy of an ideal gas, things change possibly for you. You probably have never seen this. Now, remember the definition of temperature. Temperature is the average kinetic energy of a group of molecules. Keyword emphasis on average. Now, if we actually want to, though, get from kinetic energy in joules to temperature in Kelvin, P.S. in case you haven't noticed, this entire section of notes, all of our temperatures are in Kelvin. The only reason we got away with degrees Celsius for our Q equals delta Q equals MC delta T was because of the delta T part, the change in the temperature, because 1 degree change in Celsius equals 1 Kelvin change. All right, so that's the only reason. But when in doubt, convert to Kelvin. That's going to be very, very important. Now, kinetic energy, average kinetic energy of a group of molecules equals 3/2 times Boltzmann constant times the temperature in Kelvin. So if you know the temperature, you can actually figure out the average kinetic energy of those particles. In other words, on average, what is the kinetic energy of one of those particles? So if life were ideal and we didn't have some moving faster and some moving slower, that this equation right here would actually allow you to calculate the kinetic energy of a molecule. Another way to put this, if we recognize Boltzmann's constant is actually the gas constant divided by Avogadro's number, we can just simply rearrange over here to have that equation. Now I'm going to scroll past this section. I'm going to come back to it here in a moment and talk about total internal energy of a gas. Now remember, for a gas, the molecules are separated out so far that we are neglecting the intermolecular forces. What that means is all of the energy in the gas, internal energy, is due to the kinetic energy, also known as the thermal energy, not the potential energy of the bonds. So no potential energy there. So if we're looking at total internal energy is the kinetics, aka thermal, plus the potential, aka bonds, added together. Forget the bonds whenever it comes to a gas, it's all thermal. So all the energy that it has is due to the kinetic. So if we're looking for the total internal energy of the gas, come back up to this equation for kinetic. This is for one molecule. How do you find it for all of them, the total? You just simply multiply by the number of molecules, right? That's the idea. It's the same equation, just with a number of molecules there. If we want, we could look at it through the other equation, right? And we could plug in R over Na for my Boltzmann constant. And then I recognize that the number of molecules divided by Avogadro's is the mole. And so I can substitute in lowercase n for the mole there. So a couple of easy substitutions that you can make there. Lastly, mean squared speed. How fast are those molecules actually going? What is their velocity? Simple substitution. Just put in 1/2 mv squared for your kinetic energy. If you do that, now, as you can see here, I have a velocity. You're not going to finish with a square root. You're going to leave it as squared average velocity. Reason for that, remember that velocity is a vector, and we actually don't know which direction these molecules are going. They are in random motion. Whenever you actually take a square of this average, it's going to strip off the direction. Positive squared, positive number times a positive number is a positive number. And likewise, if it was going the negative direction, negative times a negative is a positive. So squaring that vector actually strips off the direction. So we're always going to leave this as velocity squared. So if I were to solve around this form of the equation, I would leave it like that. Do not think, though, that this is like the end-all be-all equation. There's another example from the book where they solve in terms of pressure over here. That's good for you to know. And we could take this kinetic energy equation and we can substitute in 1/2 mv squared into any of it, anywhere here. And there's a lot of different substitutions and ways you can kind of mix this up, if you will. Just know, here's your base equation, kinetic energy. And then there are other substitutions that you can make, like we've talked about. Maybe saying, okay, what's the total internal energy? Let's just multiply by the number of particles that are there. Hey, what's the square velocity? Let's put in 1/2 mv squared. Okay, but